We're doing, and we'll have the next assignment out probably tonight, if not tomorrow morning. And it's going to be on Q-learning and SARSA. So it's going to be a very similar problem, but with Q-learning and SARSA, table-based again. And if you remember my last lecture, I talked about this sort of fundamental difference between on policy and off policy. And I had that example of walking across a little cliff and how you can get very different answers. So you're going to explore that a little bit. You'll get to see it very clearly. We created a problem where it's effectively what I described. You have a little cliff. You'll get to see SARSA doing something different than Q-learning. Hopefully that will be illustrative. And then so you'll be implementing those, which if you implement one, like this is the SARSA update, and this is the Q-learning update. So they're basically implementing the same thing. And then you'll be doing a concurrent version of that. And right now, I don't have a competition planned for that. I may change my mind, or may have extra credit for that. But we do have a concurrent version for you to try. And after that assignment, we'll have a deep RL assignment, which will sort of be analogous. So all of the previous lecture was very relevant to the next assignment, this Q-learning algorithm, and we'll be getting that out soon. All right, so we were just about done with this table-based value-based reinforcement learning part of the class. And we talked about SARSA, Q-learning, and different variants. The last part that we ended on was something that's actually pretty useful to know about. It's not usually done with Q-learning. Sometimes there are versions that do this with Q-learning. They're a little weird, like conceptually, but they work in practice. But the idea here is if we look at both SARSA and Q-learning and MC, Monte Carlo learning as well, they're all of this form, right? So you're always getting some experience and you're figuring out some target value, right? This is, you're using that experience to estimate, well, I think the Q value should be a little bit closer to the target, right? And the difference between the algorithms was how they chose this target. Monte Carlo just said, oh, the target is just the discounted sum of rewards that I saw after that time step. So that's just pure Monte Carlo, pure just based on what you observe. The SARSA target was a temporal difference target. And this is the extreme case. It's basically saying, well, I'm going to look at that next reward, and then I'm just going to use whatever I thought the value should be. Right, so it's a little more. They call this bootstrapping. You're bootstrapping based on what you already know or what you think you already know, and that's why it's. I always I keep telling you I think it's kind of amazing these algorithms converge because you're setting a target based on your own bad knowledge to begin with, and yet the fact that you get this one little reward in there, which is a real thing, still makes the thing converge. But these are kind of two extremes, right? This one is almost completely based on your own knowledge or misknowledge, and this one's completely based on reality. But there's going to be a lot more variance here, right? So the Monte Carlo has a lot of variance because if it's a stochastic environment, you can get different returns each time. And whereas this TD has much less variance, right? So why does it have much less variance? Would you say? Any ideas? Oh. Where does the variance come from? Up here. And why is this higher variance? Or why does it have a high variance, would you say? not a trick question. It's there's randomness in each step, right? Right. So I get a reward. I take a step. I end up in some state which could be kind of random. I get that reward. I end up in another state which could be random to some degree. And so you have this sequence of random things that can happen. You sum it up, and that's going to have higher variance than something that just has one random thing, right? Does that make sense? Yes? No? Yeah. So it's a sum of more random things here. This has just one sort of random event. You get the reward, and then the random thing is the state you end up at. But this function, this Q function, is just it's just a function. It's just a number, and so there's not as much variance in this target. In other words, if you were in state ST and you take that same action, and you look at what this value is after you do that same thing 100 times, the variance will be much less than if you're in state ST and you take the action and you generate this sequence 100 times. Okay, so one has high variance, and then the other side of the coin. Usually, when you have high variance, you have usually the trade-off is bias and variance. What that means is this is basically an unbiased estimate. Remember, we're following when we're doing SARSA, we're following a policy, a fixed policy, and this is an unbiased estimate of the return to go. Meaning that if you did this many times and you take the average, it's going to converge to the right expected value. And that's because you're actually just measuring the real system, and there's variation, but the average will converge. This is biased, meaning that at a particular point in time, if you take many samples of this quantity and you average, it may not give you the true expected return. And that's kind of clear because in the beginning, when you're following a policy and you haven't learned Q very well, it's going to be the wrong value, right? It's not going to correspond to the rest of this sequence. So it's biased but low variance, yet it still converges. So there are two extremes, and basically the idea of n-step bootstrapping is to be able to let you interpolate between those two extremes to some degree. And the idea is that you're going to pick a value n, and you're going to use the real rewards for the first n steps. Then you're going to terminate that with an estimate of the rest of the trajectory based on your Q function. Okay? So it's saying, okay, I'm going to look at the next 3 rewards, and then I'm going to use the rest of my knowledge to sort of complete the rest of the rollout, estimate the rest of the rollout. And usually, it's not actually surprising, some value of n other than 1, right? So MC corresponds to n equals infinity, or n equals the maximum length of a trajectory, and SARSA is 1. Often a value that's not 1 or infinity will be better. That's not surprising because there's a lot of possible values there, and so that's what makes this a useful trick to have. So it takes some amount of reality, but not too much, because if you have long sequences, the variance is really high. But maybe if you just look at the next 3, it's not too bad. And then you terminate with something that's biased but very low variance. So you can just use this target in an RL loop for SARSA or Monte Carlo with no problem at all. So they have an entire chapter on this in the book. You can read about it. I'm not going to talk much more about it here. If you've heard about something called SARSA lambda, that's an algorithm in the book. That's where they're saying, but you don't have to pick one value of n. Why don't we just use all values of n and sort of do some averaging of the targets that you get for each value of n? And the averaging they do is a weird type of exponential averaging using a lambda parameter. And really that's for convenience purposes. There's not really a good theoretical reason for it. But that's another thing that will be in that chapter, and it's called Sarsa lambda. So this lambda parameter kind of interpolates, how much you are like MC versus how much you're like TD. All right, so any questions about n-step bootstrapping? It can help, and in most, I mean, even deep RL algorithms, they'll have this concept because, actor-critic algorithms, as we'll see, that estimate the value function to help the policy gradient approach, they'll often use a value of n that's not 1 or infinity. So that's a trick that they'll use. All right, so we all set? Right, you know table-based reinforcement learning now. You'll be doing this for your assignment, and now you've got the slides. I don't think it's worth going over this. The main point is all of these algorithms, if you understand value iteration and policy iteration, they're just stochastic approximations, right? And hopefully the slides sort of made that clear. And knowing that lets you kind of think about little design choices of your own, right? Once you know this space, there's a lot of other types of variations that you could try that sort of fit this framework. All right, and that's it for this part. Now we're going to move to ways of doing RL for really large action state spaces that you can't enumerate in a table. And this is where the if you hear people talking about deep RL, this is where that falls. Although deep RL covers, you could say, two main classes. Let's say that function approximation for RL, there's two main classes. There's going to be value-based methods that learn a value function or Q function, and then policy-based methods that usually are focused on trying to learn a policy directly. And we'll talk about those later. And they've got deep RL versions of both of those. But the deepness only comes into play in that you're going to insert a neural network for the function approximator as opposed to something else. So in these slides, I'm going to start off focusing on just linear function approximators because that's simple. And then the last slide we'll say, hey, you can also put in the gradient of a neural network and things will be just the same, right? And then that will be called deep RL. All right, so large state spaces, so at some point, the table, just like for your value iteration stuff, maybe we can handle 1 million states, but at some point you just can't handle it, right? It's not gonna work out. Although I've seen people work hard, and they've handled. I forget the guy at Berkeley what he was handling, but they were trying to develop something for a collision avoidance system for this flight controller. So this is something that all planes have, and it's it's a pretty simple problem in some sense. But when planes are very likely to collide unless something happens, something will take over to make them avoid colliding. And there's a whole rule-based system for how this software worked. And somebody at Berkeley in the aerospace department actually formulated this problem as an MDP with a giant state space and solved it optimally using value iteration. And he was well into the hundreds of millions of states. It took a long time to compute, but at the end of the day, they had this giant policy in a table that they could hand off to the software. And it took them a long time to get this to be something that they would actually use. because these things are they have to be validated by many entities, but eventually they did. So that was a really interesting case, and if they hadn't used something like value iteration, instead used reinforcement learning, I don't think they ever would have been able to get this sort of validated. Because at least with value iteration, you can say, well, here's the problem we solved, and we solved it, right? We actually solved it optimally, right? Here's the table for the solution, and here's kind of you can try to verify whether the solution algorithm was correct. But at least you know what you solved and you can describe it to somebody. Whereas reinforcement learning, maybe table-based will converge to something, but otherwise you don't quite know exactly what the policy has solved, right? You're hoping it solved things, but there might be something off in a corner of your simulator where the thing takes a nosedive, and who knows. So I think having the actual planning, the provably optimal solution to a problem is very important in many cases, because at least you can say what you're solving, what the solution is solving. So that's an interesting use case for the type of thing that you just did for your assignments. Even though it seems, we'll never use this stuff, I do think that there's a place for it. But here, they were able to get that problem solved, but if it had been 100 billion states, probably not. They wouldn't have been able to use that approach. And so now, what do we do when that's the case? Because you'll never have enough training data. You can't even store the whole matrix of values. So what do you do? And this is just, it's kind of obvious, right? Humans don't store a table of every situation that they could be in their heads, right? We generalize and abstract really well across different situations. So right now I'm standing here talking, and we're going through lots of situations, but they're pretty much all the same, right? From like my point of view and your point of view, things are moving in the world, but most of them don't matter. So basically, function approximation is going to basically be about trying to get the system to model the similarity between situations. And then if you can do that somehow and you learn about one situation, it's going to give you information about another situation which you may have never experienced. And that's called generalization. And that can be good. It can also be dangerous because it's often very hard to say how the thing generalizes. And so you got to be very careful with this stuff. And we'll talk about that as we go. Basically the idea is we've learned how to learn V and Q. And we store them as tables. Instead, you've all had experience of representing functions in a compact way, like a linear equation. You have two numbers. If it were just in a 1D equation, two numbers describes the whole infinite space, right? And so we're going to now represent V and Q with some parameters and a functional form that takes those parameters and defines a function for the whole space. And the number of parameters is going to tend to be exponentially smaller than the number of states that the function can range over. Okay? And so there's this exponential decrease in what you have to store and learn over. And the art is picking that space of functions and the parameterization so that your problem can actually come up with a good solution. So that's all there is here. So we're going to learn the parameters from experience rather than learning each individual table entry. So I'm going to start off talking about linear function approximation. Not all of you have taken deep learning or neural networks. And linear function approximation is really the most basic type of function approximation you might do. And it's also the one that I would tend to recommend if you have the right features for your problem, because it's very simple. You're going to have a lot less issues in terms of convergence, and so it's just a good idea to. I always like to start off with linear, um, and partly it's to avoid embarrassment. There's been examples of lots and lots of people doing deep RL on certain robotics problems. And then somebody coming around, a year later and saying, "Hey, my linear network does this just as well as your really large deep network." And so it's always good to start with a linear function and prove to yourself that there's value in adding complexity. Because when you add complexity, it always becomes harder to debug, to develop, and understand what you get at the end. Linear is maybe the most interpretable of all the representations. Like, we're very used to thinking about that. So let's see what a linear function is. A lot of you know this material, so you'll just have to bear with me. We have some difference in backgrounds here. I don't require machine learning. But we're going to say that we have a set of features to start with. And these features are just features of the state that describe useful things about the state. So things about the state that you think are relevant to predicting the value. And so if you're writing features for a chess program, your states are chess positions, do you think it's going to be useful to give a feature that returns the color of the chessboard, the average color of the chessboard? Is that going to be a useful feature? Probably not. It seems pretty irrelevant. So something that maybe gives you the average color of the pieces on the board, maybe that's relevant because it would tell you how many pieces each side has, or the differential. You wouldn't actually use that feature, but that would be relevant. But features that give you the count of each type of piece, that's obviously useful, like how many pawns, how many queens. So these features can be anything, and this is sort of the art of feature engineering. If you're thinking of neural networks, you can really think of a neural network as, at the end of the day, it produces some features at the top and they're linearly combined, right? So it's kind of a way of doing this linear stuff, but you're also automatically inducing the features. So a linear function for a value is just going to be something like this. So we have some parameters, I'm going to call them theta in this, and we have a linear function like this, where you're just putting a weight in front of each feature. That tells you, the magnitude of the weight will tend to tell you how important that feature is, and the sign tells you whether it's positively or negatively correlated with the value. And then we have this bias term. Why do you think we need a bias term or why would we want a bias term for learning the value function? Any ideas why that might be useful?
Some features might be more valuable than others.
So you mean so why have different values for these? Or so the bias term is this. I should have said theta 0. Yeah. So theta 0 is the one that's not even associated with a feature. Why might we want a bias term for a linear function approximator that doesn't even depend on the state, right? It's just like this bias.
Like all of the states can have some type of reward. So if you have non-zero reward for all actions, then that cannot be zeros.
Yeah. So it's one way to think about it. Yeah. Any other insight? Yes.
So usually your estimate is not that accurate. So you approximate your value with the estimating into that state.
Yeah. So you're talking about just theta 0 here?
Yeah. So like initially when your estimate is not approximating the actual value, so if you just add some bias term, it will converge.
So it might be you might be able to improve. Yeah. So the bias term does help you improve the accuracy for sure. Yeah. Any other ideas about this? Yeah. Yes.
shouldn't it be able to help you reduce the overall magnitude of other thetas because you don't have to account for all the reward based on these individual, like F1, F2. You can sort of get a average to reduce how much each one varies.
Yeah, and I think that's a good way of thinking about it. So in classical regression, theta zero sort of is the mean, like it's the mean value, and the features are just kind of varying you around that mean. So a lot of times the values in a game or an environment, there's like there's some base level of value, and the different states are sort of going up and down from that base level, and you don't want to have to represent that base level in just the features, the feature combinations. That can actually be impossible in some cases because if your features, let's say they're 0 and 1, right, just binary features, and the values all sort of start at 100 and they vary around 100, it can be really hard and impossible to represent that type of function here. So think of this as just capturing the average value, and then the features are the feature weights are then trying to give you the variation around that average value. So your accuracy is limited by the features, of course, right? If you have stupid features, you won't be able to model a function well. It's worth asking, we're talking about linear predictors. Is it always possible to define features that allow for a perfect linear prediction? Right? Or we got some no's and some yeses. So who wants to try to justify a no or a yes? So I'm letting you define your own features. And I'm saying, okay, I've got a value function, and I want to know, can you define features that will allow me to give weights that perfectly model that value function? Any ideas? How would you define your features?
I mean, if my feature itself is, let's say, polynomial function or something, then it will always converge to the actual approximation, even if the actual value function is non-linear.
So let's even think of the actual value function as just a big table. Okay, so just a big vector. Okay, and we're trying to say, can we always define features, regardless of what that vector is? Can we always define a set of features that will exactly result in the linear function exactly matching each of those values? So just think of this big vector, arbitrary values, right? So how fine-grained can this linear function approximation actually be made to be? Any ideas?
Any complex value function can be represented by a Taylor series approximation, which is a sum of series. So that can be taken up as a linear function. Each feature is representing the complex term.
Taylor series might be a little heavy-handed, so because you couldn't really bound the number of terms that you need. So there's actually a simpler solution. Yes.
Every single state can get its own feature.
Yeah. So the easiest solution, and this is not a good solution. It's just sort of trying to provide some insight. You just have a feature for each state, an indicator feature, and it's true if that state's present and 0 otherwise, right? So we have if the ith feature is 1, then the ith state is present, and theta in that case would just be the value of that state, right? So you just have this being 0, and then for state 1, it has an indicator feature, and all the other features are 0, and so theta just gives you the value of that state. So it's kind of a stupid thing, but you can always define features. And what's the problem with this? Well, you have to have one feature per state. That kind of defeats the purpose of doing function approximation, right? So I said the reason we do function approximation is because we want to use many fewer parameters than states. So, yeah, theoretically you can model anything, but usually we're talking about many fewer parameters, exponentially fewer parameters than there are states. So let's go through a few examples. So here's a simple grid world, and you have a value of 10 here. And I think, yeah, this is 0, 0. So the coordinate system is calling this 0, 0. So this would be 6, 6, I guess. And you're going to get a plus 10 here and a minus 1 every time you end up in another state. So minus 1 for every action. And our features are going to be F1, which returns the x coordinate. So 0 to 6. And returns a y coordinate for the other features. So 2 features. So our value function would be something like this. Is there a good linear approximation? Can we set these weights so that you can get a perfect, no discounting, right? So the value of this state would be what? Be 9, because you could, you're here, you take 1 step, and you get 10 reward here. So every step gives a negative 1 reward. So it would be 9 here. What's the value of this state?
Are we assuming only orthogonal movement?
Yeah, up, right, left, down.
Okay.
So it would be 8, right? Because you have to move up and over, or over and up. So basically, it's kind of 10 minus the Manhattan distance, right? Manhattan distance is sort of, basically the sum of the coordinates. 10 minus the Manhattan distance from this position. And since this is 0, 0, the Manhattan distance is just the coordinates. So what values can we set here that will perfectly model this value function?
Theta 0 equal to 10, and theta 1 equals to the x coordinate, theta y equals to, or theta 2 equals to the y coordinate.
Well, we have, so we've got x and y as our features. And so we need to set theta 1, negative 1, negative 1, right, exactly. So 10, negative 1, negative 1. And this is going to start with 10 as our baseline and then subtract off the Manhattan distance, which is the sum of the coordinates. And just to make sure it's not confusing, this is 0, 0, and that's why the Manhattan distance sort of works. So your goal is at 0, 0. All right, so that's pretty straightforward. Now, if we change things, is there a good linear approximation now, would you say? Right, so same deal. So we have 9 here, right? That would be a value of 9. This would be a value of 9, value of 9, value of 9, then 8, 8, 8, 8. And it kind of dies off as you go out, right? So is there a good linear approximation to this? If you eyeball it, take a guess. Who thinks there's a good linear approximation? Who thinks there's not? Not one vote for either. So complete uncertainty. Yeah. Any ideas?
We can define the features as we like it, right?
No. So we're going to use the same features for now, just x and y.
Now it's just the Manhattan distance instead of between the current state and 0, 0, the current state and 4, 4.
Yeah, that's what it will be, but can we represent it with the same features that we used last time? Like, so where we're just using the x coordinate and the y coordinate as the features.
Whatever baseline value we have, regardless of that, we can only make the values go up or down by a certain slope in any given direction or direction, but we can't make that slope change suddenly based off of position. So I would say that there's no good linear approximation.
Yeah, and you're right. I mean, so the intuition here, so I don't have a picture of it, but this the value function, if you were to plot it, it kind of looks like a big hill, a big mountain, right? With 10 in the middle, and then you've got If you go out here, this would be 9, this would be 8, this would be 7. And so it's kind of dome shaped, or yeah, it's kind of a mountain shaped. And a linear approximator is going to be a plane, right? It's going to be a plane over this space, right? Because it's just in terms of x and y, it's going to be a plane, and you can't fit a mountain with a plane, right? You can't fit the value, so there is none. You'd have some. You could do a least squares fit, but that's the best you could do. And so we've already had somebody suggest, well, you're going to have add another feature, and that feature could be z, which is the Manhattan distance from 3,3. Right? If you add the Manhattan distance from 3,3, then you can easily, I guess I should ask, can you now create weights here that will model this value function? So what are the weights? Anybody want to give us the weights? So what would theta 0 be?
10.
10. How about theta 1? 0. Theta 2? Theta 3? Negative 1. All right. Right. So it's 10 minus the Manhattan distance. So, and this is a pretty typical thing if you have a goal-based domain or function approximation. They'll often model some measure of distance or direction from the goal, right? And this is kind of why. All right, so I think, yeah, we're just about done. But basically, we spent a lot of time just talking about the linear function approximator and what it can do. There's a lot of feature engineering that goes into these things. But what we're going to do now is figure out, well, if we're going to represent the value function this way, how do we develop an RL loop that will update the parameters, right? Rather than update something about the table of value for each state. So we're going to have this RL loop that looks very much, well, exactly like what we've seen before. Explore, exploit, then you're going to do some sort of update, but we want to update the parameters now, okay, instead of the values directly. And that's what we'll focus on next time.